every night it rises, a pale face staring down at Earth, watching over oceans and continents, over sleeping cities and restless seas. We have gazed upon it since the first humans looked upward and wondered. We have told stories about it, worshipped it, feared it, and dreamed of reaching it. And then, one day, we did. But here is the thing most people never realize. The moon is not just a beautiful light in the night sky. It is not simply a companion to our planet, circling endlessly in the darkness. The moon is a time capsule, a vault, a library written in rock and dust, holding secrets that stretch back 4.5 billion years to the very birth of our solar system. And we are only now learning how to read it. If you find yourself captivated by the mysteries of space and the stories hidden in the cosmos, take a moment to like this video and subscribe to Cosmic Drift. We journey through the universe together, exploring the wonders that surround our small blue planet. Your support helps us continue these cosmic adventures. Now, let us unlock the moon together. When you look up at the moon tonight, you are looking at something that has remained essentially unchanged for billions of years. While Earth has transformed countless times, its surface, reshaped by plate tectonics, erosion, volcanic eruptions, and the rise and fall of life itself, the moon has stayed frozen in time. Its craters from ancient impacts still look much the same as they did when they first formed. Its plains of hardened lava, the dark patches we call Maria, have sat undisturbed since they cooled eons ago. The footprints left by Apollo astronauts more than 50 years ago remain perfectly preserved, untouched by wind or rain, because there is no wind and there is no rain. The moon is a world without weather, without an atmosphere to speak of, a place where the past is not buried but displayed openly on the surface. This makes the moon invaluable to scientists. Earth constantly erases its own history. The oldest rocks on our planet are rare treasures, because most have been recycled back into the interior by geological processes. But the moon remembers everything. It carries scars from the violent early days of the solar system, when newly formed planets were bombarded by debris left over from the sun's creation. It holds clues about what conditions were like on Earth billions of years ago, before life emerged, before the oceans filled, before the continents assembled. In studying the moon, we study our own origins. The story of lunar science is really the story of human curiosity evolving over thousands of years. It begins with simple questions. What is that bright circle in the sky? Why does it change shape? Why does it seem to follow us as we walk? And it continues with questions we are still trying to answer today. Where did the moon come from? What can it tell us about the history of impacts in the inner solar system? Is there water hiding in its permanently shadowed craters? Could humans one day live there? The earliest human understanding of the moon was wrapped in mythology and religion. Ancient cultures saw faces, figures, and gods in its mottled surface. The Babylonians tracked its phases to create calendars. The Greeks proposed that it was a sphere, not a flat disk, and that its phases were caused by changing angles of sunlight. Aristotle believed the moon marked the boundary between the corrupt, changing world below and the perfect, unchanging heavens above. This view persisted for centuries, reinforced by philosophical traditions that saw celestial objects as fundamentally different from earthly matter. Then came the telescope. In 1609, Galileo Galilei turned his newly constructed instrument toward the moon and saw something that shattered centuries of assumption. The lunar surface was not smooth and perfect. It was rough and uneven, covered with mountains, valleys, and circular depressions. Galileo sketched what he saw, documenting craters and highlands with remarkable accuracy for such an early instrument. His observations were revolutionary. If the Moon had features similar to Earth, perhaps it was a place, a world, not just a celestial light. Over the following centuries, telescopes improved and lunar maps became more detailed. Astronomers named craters after famous scientists and philosophers. They measured mountains by the shadows they cast. They speculated about whether the dark areas might be seas, which is why we still call them maria, the Latin word for seas, even though we now know they are vast plains of solidified lava. But telescopes could only reveal so much. They could map the surface, but they could not explain how it formed. They could observe the Moon's motions, but they could not tell us its composition. They could inspire wonder, but not answer the deepest questions. Understanding the Moon's true nature required new tools and new approaches. In the 19th century, geologists began to recognize that craters on Earth, though rare and often obscured, were caused by impacts from space rocks. This raised an obvious question. Were the Moon's countless craters also formed by impacts? Or were they volcanic, as some scientists argued, formed by explosions from within? The debate continued for decades. Photography changed everything. The first photograph of the Moon was taken in 1840 by John William Draper, a chemist and physician who aimed a telescope at the night sky and captured an image that, while crude by modern standards, demonstrated that scientific study of the Moon could extend beyond the human eye. Over the following decades, photographic techniques improved, and detailed lunar atlases were published, providing researchers with consistent records to study and compare. But even photography had limits. We could only see the side of the Moon that faces Earth. The same hemisphere is always visible to us because the Moon rotates exactly once for every orbit it completes around our planet, a phenomenon called synchronous rotation or tidal locking. This means the far side remained a complete mystery until the space age. No telescope, no matter how powerful, could reveal what lay on that hidden hemisphere. The 20th century brought two transformations that would revolutionize lunar science. The first was the development of radioactive dating techniques, which allowed scientists to determine the ages of rocks with remarkable precision by measuring the decay of certain elements. This meant that if we could ever get lunar samples, we could find out when the Moon's various features formed. The second transformation was the space race. When the Soviet Union launched Sputnik in 1957, it demonstrated that human technology had reached a threshold. Objects could be sent beyond Earth's atmosphere. The Moon, which had seemed forever out of reach, suddenly became a destination. Danim. Both the United States and the Soviet Union set their sights on lunar exploration, driven by Cold War competition, but also by genuine scientific curiosity. The Soviet Union achieved many firsts. Lunar 1, launched in 1959, became the first spacecraft to escape Earth's gravity and fly past the Moon. Lunar 2 became the first human object to reach another celestial body, impacting the lunar surface later that same year. And Lunar 3, also in 1959, accomplished something extraordinary. It flew around the Moon and photographed the far side, revealing terrain that no human eyes had ever seen. The images were grainy and difficult to interpret, but they showed that the far side looked dramatically different from the near side. It was almost entirely highlands, with far fewer of the dark maria that dominate the face we see from Earth. This asymmetry between the two hemispheres remains one of the Moon's enduring puzzles. the American program, initially behind, would ultimately achieve the most ambitious goal of all. In 1961, President John F. Kennedy declared that the United States would land a man on the Moon and return him safely to Earth before the decade was out. It seemed almost impossible. At that point, American astronauts had barely reached space. The technology to send humans to the Moon, have them land and walk on its surface, and bring them home did not exist. It had to be invented. The effort that followed was one of the largest peacetime mobilizations in history. Thousands of engineers, scientists, technicians, and administrators worked together to solve problems that had never been faced before. How do you navigate to the Moon? How do you land softly on its surface with no atmosphere to slow you down? How do you design a suit that can protect an astronaut from the vacuum of space, the temperature extremes, and the radiation? How do you ensure they can return? Before astronauts could go, robots went first. The Ranger program sent probes that intentionally crashed into the Moon, taking photographs all the way down. These images revealed the surface in greater detail than ever before, showing that the Moon was covered in fine debris, raising concerns about whether a spacecraft would sink into a layer of dust. The Surveyor program achieved soft landings, demonstrating that the surface was firm enough to support a spacecraft and eventually an astronaut. The Lunar Orbiter program mapped the Moon from orbit, identifying potential landing sites and providing the detailed images needed to plan the crewed missions. Then came Apollo. On July 20, 1969, the lunar module Eagle separated from the command module Columbia and descended toward the Sea of Tranquility. Commander Neil Armstrong and lunar module pilot Buzz Aldrin watched through the small windows as the surface grew closer. Armstrong took manual control when he saw the planned landing site was covered with boulders, guiding the craft to a smoother area while the fuel ran low. At last, a contact light, then silence, then words that echoed around the world. The Eagle has landed. Hours later, Armstrong descended the ladder and became the first human to set foot on another world. His words, chosen carefully, spoke to the moment's significance for all of humanity. Aldrin followed, and together they spent about 2.5 hours outside the spacecraft, collecting samples, setting up experiments, and planting a flag. They left behind scientific instruments that would transmit data back to Earth and took with them rocks and dust that scientists would study for decades. Apollo 11 proved it could be done. 5 more missions would land astronauts on the Moon over the next 3.5 years. Apollo 12 demonstrated precision landing by touching down within walking distance of an earlier robotic probe. Apollo 13 became famous not for what it achieved on the Moon, but for the heroic effort to bring its crew home safely after an oxygen tank explosion crippled the spacecraft. Apollo 14 landed in a more challenging region and brought back samples from a different geological setting. Apollo 15, 16, and 17 were extended missions that included lunar rovers, allowing astronauts to explore much greater distances and collect far more samples. Each mission added to our understanding. Each landing site was chosen for its scientific value, representing different types of terrain and different geological histories. The astronauts were trained in field geology, so they could recognize interesting rocks and make intelligent decisions about what to collect. They also deployed instruments that measured heat flow from the lunar interior, detected moonquakes, analyzed the composition of the thin wisps of gas that pass for a lunar atmosphere, and reflected laser beams from Earth to precisely measure the distance between the two bodies. When the last Apollo mission departed in December 1972, astronauts Eugene Cernan and Harrison Schmitt left behind more than footprints and flags. They left a legacy of scientific discovery that continues to this day. The samples brought back by Apollo, totaling over 800 pounds of lunar material, are still being studied. Techniques that did not exist in the 1970s now allow scientists to extract new information from these ancient rocks. Every few years, some of the carefully preserved samples are opened for the first time, reserved for future generations of researchers with tools their predecessors could not have imagined. So what did we learn? What secrets did the moon reveal? The most profound discovery concerned the moon's origin. Before Apollo, there were three main theories. Perhaps the moon formed alongside Earth, from the same cloud of gas and dust, like a sibling. Perhaps it was once a separate body that was captured by Earth's gravity as it wandered past. Perhaps Earth spun so rapidly in its youth that a chunk of material flung off and became the moon. Each theory had problems. None quite fit the evidence. The Apollo samples changed everything. When scientists analyzed the lunar rocks, they found that the moon's composition was similar to Earth's mantle, but different from Earth's overall composition. The moon has far less iron than Earth does. It also lacks certain volatile elements that should be present if it formed from the same original material. But it shares distinctive isotopic signatures with Earth, indicating a deep connection between the two bodies. These findings pointed toward a dramatic scenario. What if, early in the solar system's history, a Mars-sized body collided with the young Earth? The impact would have been catastrophic, far beyond anything we can imagine. Enormous amounts of material would have been blasted into orbit around our planet. This debris, a mixture of material from both Earth and the impactor, would have gradually coalesced to form the moon. This giant impact hypothesis explains why the moon's composition is similar to Earth's outer layers, but not identical to Earth as a whole. The impactor, sometimes called Theia, contributed its own material to the mix. The collision also explains why the moon has such a small iron core, since most of the iron from both bodies had already sunk to their centers before the impact and would have merged into Earth's core rather than being ejected into orbit. The idea was shocking at first. The notion that a collision of such violence had shaped our planet and created our constant companion seemed almost too dramatic to be true. But over the decades, the evidence has continued to accumulate. Computer simulations show that such an impact could indeed produce a moon with the right size, composition, and orbit. The giant impact hypothesis is now widely accepted, though researchers continue to refine the details. Was the impact a glancing blow or a head-on collision? How much mixing occurred between the materials of the two bodies? These questions drive ongoing research. The Apollo missions also revealed the moon's geological history in unprecedented detail. By determining the ages of different rocks, scientists could construct a timeline of lunar events. The oldest rocks, found in the Bright Highlands, date to about 4.5 billion years ago, close to the age of the solar system itself. These ancient crustal rocks crystallized from an early magma ocean that covered the young moon shortly after its formation. The moon, born from the heat of the giant impact, would have started as a molten ball, gradually cooling and solidifying from the outside in. The large impact basins, the circular scars left by enormous asteroids and comets, formed mostly during a period called the Late Heavy Bombardment, roughly 3.8 to 4 billion years ago. During this time, the inner solar system was swept by a storm of debris, possibly triggered by gravitational interactions Among the outer planets that sent rocks careening through the system, Earth was hit just as hard, but the evidence has been erased by geological activity. The Moon preserves the record. The Dark Maria formed later, as volcanic eruptions flooded the impact basins with lava. These eruptions occurred primarily between 3.5 and 3 billion years ago, though some lavas may be younger. The lava came from deep within the Moon, where radioactive decay generated enough heat to melt rock. But the Moon is small, and it cooled faster than Earth. Volcanic activity eventually ceased, leaving the Maria as monuments to a more active past. Since about 3 billion years ago, the Moon has been geologically quiet. Occasional impacts still occur, adding new craters to the ancient surface. But the internal heat engine has shut down. The Moon today is essentially dead, a world frozen in time. Its surface a record of events from the solar system's violent youth. Yet the exploration did not end with Apollo. After the crewed mission stopped, robotic spacecraft continued to study the Moon from orbit and from the surface. The Soviet Lunar program achieved automated sample return missions, bringing back small amounts of lunar material without risking human lives. The Lunar rovers explored the surface, controlled remotely from Earth, demonstrating technologies that would later be refined for Mars exploration. Then came a hiatus. For almost 2 decades, no new missions visited the Moon. The space race was over, budgets were tight, and attention turned elsewhere. Mars became the new frontier, with probes mapping its surface and searching for signs of water and life. The Moon, it seemed, had given up its secrets, but appearances were deceiving. In the 1990s, interest in the Moon revived. A small spacecraft called Clementine, built as a test of new sensor technologies, mapped the Moon in multiple wavelengths and made a tantalizing discovery. Data from the spacecraft suggested the possible presence of water ice in permanently shadowed regions near the lunar poles. This was unexpected. The Moon was supposed to be bone, dry, every drop of water long since evaporated into the vacuum of space. The idea that water might exist on the Moon had profound implications. Water is essential for human life. It can be split into hydrogen and oxygen for breathing and for rocket fuel. If astronauts could access lunar water, they would not have to carry all their supplies from Earth. The Moon could become not just a destination, but a waypoint, a place where explorers could refuel before heading deeper into space. Subsequent missions added evidence. The Lunar Prospector spacecraft, launched in 1998, carried instruments specifically designed to detect hydrogen, a telltale sign of water. It found elevated hydrogen concentrations near the poles, consistent with the presence of ice. But the evidence was indirect. The hydrogen could come from water, but it might have other sources, such as the solar wind implanting hydrogen atoms into the lunar soil. A dramatic experiment was conducted at the end of Lunar Prospector's mission. The spacecraft was deliberately crashed into a permanently shadowed crater near the South Pole, with telescopes on Earth and in orbit watching for a plume of debris that might contain water vapor. The results were inconclusive. No water was detected, but that did not rule out its presence, since the impact might have been too small or the conditions unfavorable. The next decade brought a wave of new missions from multiple countries. Japan, China, India, and Europe joined the exploration of the Moon, sending orbiters to map the surface in detail and study the lunar environment. These missions confirmed and extended earlier findings. The Moon's surface is covered with a layer of broken rock and dust, called regolith, created by billions of years of impacts. This regolith contains valuable resources, including oxygen locked in minerals, helium-3 implanted by the solar wind, and potentially water ice in the shadowed craters. In 2009, NASA sent 2 spacecraft to the Moon on a single rocket. The Lunar Reconnaissance Orbiter would map the surface in exquisite detail from orbit, identifying potential landing sites and characterizing the radiation environment that future astronauts would face. The Lunar Crater Observation and Sensing Satellite, known as LCROSS, had a different purpose. It would deliberately crash a spent rocket stage into a shadowed crater near the South Pole, and then fly through the resulting debris plume to analyze its composition before crashing itself. The target was Cabeus Crater, a dark pit near the South Pole where sunlight never reaches the floor. On October 9, 2009, the Centaur upper stage struck the crater at over 5,000 miles per hour. LCROSS followed 4 minutes later, its instruments recording data that was transmitted back to Earth in real time. The results were definitive. Water was detected in the debris plume. Not just traces, but significant amounts. The permanently shadowed regions of the Moon contained water ice mixed with the regolith. This discovery changed how we think about the Moon. Far from being a completely dry world, the Moon harbors frozen water in its coldest, darkest places. This water likely comes from multiple sources. Some may have been delivered by comets and asteroids over billions of years. Some may form through chemical reactions when solar wind hydrogen interacts with oxygen in lunar minerals. However it got there, its presence opens new possibilities for exploration. But water is not the only resource that makes the Moon interesting for future missions. The lunar soil contains oxygen, locked in minerals that make up the regolith. With enough energy, this oxygen can be extracted and used for breathing or propulsion. The Moon also lacks an atmosphere, which has both disadvantages and advantages. There is no air to breathe, obviously, and no protection from radiation or micrometeorites. But there is also no interference for telescopes. Radio observatories on the far side of the Moon would be shielded from Earth's noisy electromagnetic chatter, able to listen for faint signals from the early universe that are impossible to detect from our planet. Optical telescopes would have perfectly clear skies, never clouded by weather. The scientific potential is enormous. A permanent presence on the Moon could enable long-term experiments that are impossible to conduct from Earth or even from orbit. Astronomers dream of large telescopes on the lunar surface. Physicists imagine laboratories where the low gravity and high vacuum allow experiments that would be impractical anywhere else. Geologists want to explore regions that the Apollo astronauts never reached, collecting samples that could answer questions about the Moon's history that remain open. And there are commercial possibilities as well. Some visionaries speak of mining the Moon for helium-3, a rare isotope that could theoretically fuel future fusion reactors. Others imagine extracting metals or manufacturing materials in the lunar environment. The feasibility of these schemes remains uncertain, but the discussion itself shows how far our thinking about the Moon has evolved. We have gone from wondering what that light in the sky might be to planning how we might live and work there. The arc of lunar science stretches across millennia, from the first people who noticed patterns in the Moon's phases, to the astronauts who walked on its surface, to the robots that continue to explore it today. And the story is far from over. The new chapter of lunar exploration is already underway. In 2019, China achieved something remarkable. The Chang'e 4 mission became the first spacecraft to land on the far side of the Moon, setting down in the ancient Volcanic crater within the vast South Pole Aitken Basin. This basin is one of the largest and oldest impact structures in the entire solar system, a scar from a collision so violent that it may have excavated material from deep within the Moon. Landing there required a relay satellite positioned beyond the Moon to maintain communication, since direct signals from the far side cannot reach Earth. The Chang'e 4 lander carried a small rover named Yutu-2, which has been exploring the crater floor ever since, analyzing rocks and soil that have never before been examined up close. The mission has returned scientific data about the subsurface structure of the regolith and the mineral composition of the landing site. Perhaps most remarkably, it also carried a small sealed container containing seeds and silkworm eggs, an experiment to see if life could survive in the harsh lunar environment. Cotton seeds sprouted briefly before succumbing to the cold of the lunar night. China followed this success with Chang'e 5 in 2020, which accomplished the first sample return mission since the Soviet era. The spacecraft collected about 4 pounds of lunar material and brought it back to Earth for analysis. Initial studies revealed that these samples came from volcanic rocks much younger than the Apollo samples, only about 2 billion years old. This was surprising. Scientists had thought that lunar volcanism had largely ended by 3 billion years ago. The Chang'e 5 samples show that at least some volcanic activity continued much longer, raising questions about the Moon's thermal evolution. India, too, has joined the lunar explorers. The Chandrayaan program has sent orbiters and landers to the Moon, with Chandrayaan-1 making the significant discovery that confirmed water molecules are present across the lunar surface, not just at the poles. The water concentration is extremely low, far less than in the driest deserts on Earth, but it is there, likely cycling between the surface and the thin envelope of gases around the Moon. Private companies have also entered the picture. Once the exclusive domain of national space agencies, lunar exploration is becoming accessible to commercial ventures. Several companies are developing robotic landers to deliver payloads to the Moon, from scientific instruments to commercial technology demonstrations. This emerging lunar economy could transform how we think about space exploration, shifting from government-led expeditions to a more diverse ecosystem of public and private efforts. All of this sets the stage for the next great leap in lunar science, the return of humans to the Moon through NASA's Artemis program. Artemis takes its name from the twin sister of Apollo in Greek mythology, a fitting choice for a program that aims to build on Apollo's legacy while charting new territory. The program's goals are ambitious, not just to land astronauts on the Moon again, but to establish a sustainable presence there, not just to visit, but to stay. The Artemis program plans to land the first woman and the first person of color on the Moon, symbolizing how space exploration has evolved since the Apollo era. But symbolism is only part of the story. The scientific objectives are substantial. Artemis missions will target the lunar South Pole, where water ice hides in permanently shadowed craters and where ancient rocks might hold clues to the earliest history of the inner solar system. The Artemis architecture involves several components working together. The Space Launch System, the most powerful rocket ever built, will send astronauts beyond low Earth orbit in the Orion spacecraft. A small space station called Gateway will orbit the Moon, serving as a staging point for missions to the surface. And new human landing systems, developed in partnership with commercial companies, will carry astronauts down to the surface and back up to orbit. The scientific payloads for Artemis missions are still being developed, but the priorities are clear. understanding the distribution and origin of lunar water ice is essential for future exploration. Determining the age and composition of the South Polar terrain will fill gaps in our knowledge of the Moon's geological history. Deploying instruments to characterize the radiation environment, the thermal conditions, and the properties of the regolith will help engineers design better habitats and systems for long-term stays. And there is something else. The Moon will serve as a proving ground for technologies needed to explore Mars and beyond. Learning to live and work on another world, even one relatively close to home, teaches lessons that cannot be learned on Earth or in low orbit. The psychological challenges of isolation and confinement, the engineering challenges of extracting resources and recycling waste, the operational challenges of conducting complex tasks in spacesuits under alien conditions. Every Apollo mission pushed boundaries, but the total time spent on the lunar surface across all 6 landings was less than 2 weeks. Artemis aims for sustained campaigns, building knowledge and capability over years. Let us step back now and consider what we have learned about the Moon itself, this companion that has traveled with Earth for billions of years. The Moon is not simply a rock. It is a world with its own geological history, its own structure, its own story to tell. Deep within lies an iron core, much smaller relative to the Moon's size than Earth's core is to our planet. This small core is one reason the Moon lacks a global magnetic field today, unlike Earth with its protective magnetosphere. But there are hints that the Moon once had a magnetic field, early in its history, when the core was hotter and more dynamic. Certain ancient rocks show evidence of being magnetized by a field that no longer exists. Surrounding the core is a mantle of silicate rock, similar in composition to Earth's mantle, but with important differences. The Moon's mantle appears to be more uniform, less chemically differentiated than Earth's. This is consistent with the idea that the Moon formed from debris that was already partly processed by the giant impact, rather than from a completely mixed primordial material. Above the mantle lies the crust, a layer of lighter rock that floated to the top when the Moon was molten. The crust is thicker on the far side than on the near side, which may explain why the maria are concentrated on the near side. When large impacts struck, they excavated basins that penetrated the crust more deeply on the thinner near side, allowing magma from below to rise and flood the basins. On the far side, the thicker crust prevented most magma from reaching the surface. The surface itself is covered by regolith, a blanket of broken rock and dust created by billions of years of impacts. On the maria, the regolith is typically a few meters deep. In the highlands, it can extend tens of meters down. This layer contains a record of the Moon's history, including tiny glass beads formed by impacts, mineral grains from diverse sources mixed together, and implanted atoms from the solar wind. Studying the regolith is like reading a mixed-up library, with pages from many different books shuffled together. The temperature on the Moon swings wildly. During the lunar day, which lasts about 2 weeks, the surface can reach 127 degrees Celsius, hot enough to boil water. During the equally long lunar night, temperatures plummet to minus 173 degrees Celsius, colder than any place on Earth. This extreme range poses challenges for equipment and would pose challenges for human habitation. Surviving the lunar night requires substantial power reserves to maintain heat, but some places on the Moon experience perpetual extremes. At the poles, certain crater floors never see sunlight because the sun always remains near the horizon at these latitudes. These permanently shadowed regions are among the coldest places in the solar system, with temperatures that can drop below -240 degrees Celsius. These deep freezes are where water ice accumulates and persists, preserved against the ravages of solar radiation that would otherwise break water molecules apart. In contrast, certain elevated points near the poles receive nearly continuous sunlight, with only brief periods of darkness. These peaks of eternal light are prime real estate for future bases because solar panels there could generate power almost continuously, reducing the need for other energy sources. The Moon has no atmosphere to speak of. What exists is technically called an exosphere, a thin envelope of atoms and molecules so sparse that they rarely collide with each other. Atoms are released from the surface by impacts, solar winds sputtering, and thermal processes, but they quickly escape into space because the Moon's gravity is too weak to hold them. This means there is no weather, no wind erosion, no oxidation. Everything that happens on the Moon is preserved in a way that would be impossible on Earth. This preservation extends to footprints and tire tracks, but also to ancient phenomena. The Moon preserves a record of the solar wind over billions of years, particles embedded in the soil that tell us about the history of the Sun. It preserves meteorites from elsewhere in the solar system, rocks that landed on the Moon and have remained essentially unaltered since. Some researchers have even speculated that the Moon might preserve material from early Earth, blasted off our planet by large impacts and deposited on the lunar surface, where it could survive in ways it never could on our geologically active world. The lack of atmosphere also means the Moon is exposed to cosmic radiation and solar energetic particles. This radiation poses a health risk for astronauts spending extended time on the surface. Shielding is essential, whether from specialized materials, regolith piled over habitats, or underground facilities in lava tubes. Lava tubes are one of the Moon's most intriguing features. When lava flows across a surface, the outer layer can cool and solidify, while molten rock continues flowing beneath. When the eruption ends and the remaining lava drains away, a hollow tube is left behind. Earth has lava tubes, but they tend to collapse over geological time. The Moon's lower gravity and lack of erosion allow tubes to persist much longer and grow much larger. Some lunar lava tubes may be kilometers wide and tens of kilometers long, vast underground caverns that could shelter entire habitats from radiation, temperature extremes, and micrometeorite impacts. Several pits on the lunar surface have been identified as possible skylights into lava tubes, places where the roof has collapsed, providing potential access points. Future missions may explore these features to determine their suitability for human habitation. Living underground on the Moon might sound like science fiction, but it may be the most practical solution for long-term settlement. The Moon also experiences seismic activity, though not in the way Earth does. There are no tectonic plates on the Moon, no subduction zones or spreading ridges. Instead, moonquakes come from several sources. Deep moonquakes occur hundreds of kilometers below the surface, triggered by tidal stresses as Earth's gravity flexes the lunar interior. These deep events are small and predictable, following patterns related to the Moon's orbit. Shallow moonquakes occur closer to the surface and can be more powerful, though still modest by terrestrial standards. Their cause is less well understood. Thermal moonquakes occur when the lunar surface warms dramatically at sunrise after the cold of night, causing rocks to expand and crack. And impact events generate seismic waves when meteoroids strike the surface. The Apollo seismometers operated for years after the astronauts left, recording thousands of moonquakes and building a picture of the lunar interior. This data revealed the layered structure of core, mantle, and crust, though many details remain uncertain. Future seismic networks could refine this picture considerably. Understanding the Moon's interior matters for more than academic reasons. The structure and composition of the lunar interior hold clues to the formation of rocky worlds throughout the solar system and beyond. By studying the Moon up close, we learn principles that apply to planets around other stars, worlds too distant to visit, but not too distant to understand. Let us turn now to one of the most captivating mysteries of the Moon, its relationship to life on Earth. We know that the Moon influences our planet in profound ways. The most obvious is the tides. The Moon's gravity pulls on Earth's oceans, creating bulges of water on both the near side and the far side. As Earth rotates beneath these bulges, coastlines experience high and low tides in a rhythm tied to the Moon's position. The Sun also contributes to tides, but the Moon's influence is stronger because it is so much closer. Tides may seem like a simple phenomenon, but they have shaped the history of life on Earth in subtle ways. The regular rise and fall of water at coastlines creates intertidal zones, environments where organisms must adapt to periodic exposure to air and submersion in water. These challenging habitats may have served as evolutionary bridges between marine and terrestrial life. Some researchers have speculated that tidal pools could have played a role in the origin of life itself, concentrating organic molecules and cycling conditions in ways that promoted chemical evolution. The Moon also stabilizes Earth's axial tilt. Our planet is tilted about 23.5 degrees relative to its orbital plane, and this tilt is responsible for the seasons. Without the Moon's gravitational influence, Earth's tilt could vary chaotically over millions of years, swinging from nearly zero to extreme angles. Such variations would cause dramatic climate changes, potentially making the planet inhospitable to complex life. Mars, which lacks a large moon, has experienced such axial wanderings, with profound effects on its climate history. The Moon's gravitational tug also slows Earth's rotation over time. Early in the Moon's history, the day was much shorter, perhaps only a few hours long. Tidal friction has gradually transferred angular momentum from Earth's rotation to the Moon's orbit, lengthening our days and pushing the Moon farther away. The Moon recedes from Earth by about 3.8 centimeters per year, a rate confirmed by laser measurements, bouncing off reflectors left by Apollo astronauts. In the distant past, the Moon was much closer and loomed much larger in the sky. The tides would have been dramatically stronger, perhaps flooding vast areas of early continents. The shorter days would have meant faster winds and different circulation patterns in atmosphere and ocean. The Earth-Moon system 4 billion years ago would have been a very different place from what we know today. And in the distant future, the Moon will continue to recede until Earth's rotation slows enough to match the Moon's orbital period. At that point, billions of years from now, Earth and Moon will be locked face to face, each showing the same side to the other forever. But that future is unimaginably remote, longer than the remaining lifetime of the Sun as we know it. The Moon's influence on Earth extends beyond physics to culture and psychology. For as long as humans have existed, the Moon has been a constant presence, a marker of time, a symbol in art and religion, a muse for poets and dreamers. Lunar calendars predate written history. Festivals and rituals around the world are tied to the Moon's phases. The very word month derives from moon, a reminder that our units of time are built on lunar cycles. The Moon's changing appearance, waxing from new to full and waning, back again, has inspired countless interpretations. Birth and death, growth and decay, hope and loss, all have been read into the monthly progression of phases. The full moon has been associated with madness, hence the word lunatic, though modern studies find little evidence that human behavior actually changes with the lunar cycle. Still, the perception persists, a testament to the deep psychological imprint the moon has left on our species. And then, there is the simple fact that the moon is reachable. Among all the worlds in the universe, the moon is the one we have touched. Humans have walked there. We have picked up rocks and brought them home. We have left behind instruments and flags and footprints that will persist for millions of years. The moon is no longer just a light in the sky or a symbol in mythology. It is a place, and we have been there. That knowledge changes something. Knowing that ordinary people, mortal and flawed, have stood on another world and looked back at Earth expands our sense of what is possible. The moon is close enough to visit in a few days, yet far enough to be an alien environment, a place without air or rain where the sky is always black, and Earth hangs in the silence like a blue and white marble. The astronauts who saw this view spoke of it with awe. Many were transformed by the experience, returning with a deeper appreciation for Earth's fragility and a conviction that the boundaries dividing humanity seemed arbitrary from that distance. The moon continues to influence science and exploration today, even as we plan for missions beyond. It serves as a testbed for technologies that will eventually go to Mars. It offers a unique vantage point for astronomy. It holds resources that could enable deeper exploration, and it keeps its secrets close, revealing new mysteries even as old ones are solved. Consider, for instance, the mystery of the lunar swirls. Scattered across the moon's surface are peculiar bright markings that seem to swirl and curve across the landscape, patterns unlike anything else on the lunar surface. The most famous example is Gamma, a complex pattern in the ocean of storms that looks almost painted onto the regolith. These swirls have puzzled scientists for decades. What causes them? The leading explanation involves localized magnetic fields. Unlike Earth, the moon has no global magnetic field, but certain regions retain patches of magnetism, relics from the moon's magnetically active past, or perhaps created by ancient impacts. These local magnetic fields might deflect charged particles from the solar wind, protecting the surface beneath them from the weathering processes that darken the regolith over time. The protected areas remain lighter, creating the swirl patterns, but questions remain. Why are the magnetic anomalies shaped the way they are? How did they form? Why do some magnetized regions have swirls while others do not? Each answer leads to new questions, a pattern familiar to anyone who has studied the moon. Another mystery concerns the origin of the lunar dichotomy, the stark difference between the near side and the far side. As we mentioned, the near side is dominated by the dark Maria, while the far side is almost entirely bright highlands. This asymmetry cannot be explained by chance. Something about the moon's history or structure must account for it. One possibility is that the crustal thickness varies due to how the moon solidified after the giant impact. If the near side was warmer, perhaps heated by Earth's radiation or by tidal effects, the crust might have formed thinner there. Thinner crust would make it easier for lavas to reach the surface when impacts excavated the large basins. Another possibility involves a second moon. Some researchers have proposed that early in the moon's history, a smaller companion orbited alongside it. Over time, this smaller body spiraled inward and collided with the moon in a slow-motion impact, adding extra crustal material to one hemisphere. The far side would then be thicker because it received this additional layer. Neither explanation is proven. The dichotomy remains one of the Moon's enduring puzzles, a reminder that even a world we have walked upon still holds surprises. The Moon also preserves a record of impacts that can tell us about conditions throughout the inner solar system. By counting craters and measuring their sizes, scientists can estimate the rate at which objects struck the Moon at different times in history. This cratering record suggests that the early solar system was a violent place, with impacts far more common than they are today. The rate decreased over time as debris was swept up, but significant impacts continued for billions of years. One particularly interesting question is whether the impact rate was constant or varied. Some evidence suggests a spike in impacts around 4 billion years ago, the late heavy bombardment mentioned earlier. If this spike occurred, it implies that something destabilized the orbits of asteroids and comets, sending them careening into the inner solar system in a relatively brief pulse. The gravitational effects of the giant planets, particularly Jupiter and Saturn, are the most likely culprits. As these planets migrated to their current positions, they would have scattered smaller bodies throughout the system, but the late heavy bombardment remains controversial. Some researchers argue that the evidence has been misinterpreted, that the apparent spike is an artifact of how we date samples or how we count craters. The Moon's rocks hold the answer, but more samples from more locations are needed to settle the debate. The Apollo samples, as valuable as they are, came from a limited set of locations, all on the near side, all relatively close to the lunar equator. The polar regions remain unsampled by crewed missions. The far side has only been touched by robotic probes. The South Pole Aitken Basin, one of the oldest and largest impact structures known, could hold rocks from deep within the Moon's mantle, material excavated by the tremendous collision that formed the basin. Retrieving samples from these locations is a high priority for future missions. Beyond the specific rocks themselves, there is value in understanding the broader context. Where exactly does each sample come from? What is its relationship to surrounding terrain? Astronauts, with their ability to observe, adapt, and make judgments on the spot, are vastly better at this kind of geological fieldwork than robots. The Apollo astronauts, trained extensively in geology, made observations and collected samples that a robotic arm could never have selected. Future astronauts will do the same, but in new locations with new questions. The technological advances since Apollo are remarkable. Communications are faster and more reliable. Sensors are more sensitive and more compact. Computing power that once filled rooms now fits in a pocket. These improvements will make future lunar exploration more productive than ever, even as the fundamental goals remain the same. To understand where the Moon came from, what it can tell us about the history of our cosmic neighborhood, and what it might offer for humanity's future. Let us delve deeper into one of the most tantalizing possibilities: lunar water. Water on the Moon exists in several forms. The most dramatic is the ice in permanently shadowed craters, but that is not the only source. Observations from orbit have detected hydroxyl, a molecule consisting of one hydrogen atom bonded to one oxygen atom, distributed across the lunar surface. This hydroxyl is most abundant at high latitudes and in the morning and evening, suggesting it forms through chemical reactions with the solar wind and migrates across the surface in response to temperature. Some of this surface water may accumulate in the cold traps at the poles over geological time. Imagine a slow but steady drip, molecules migrating from warmer regions to colder ones, gradually building up deposits of ice in the darkness. The process would be incredibly slow by human standards, but significant over billions of years. The water in permanently shadowed regions appears to be mixed with the regolith, rather than existing as solid ice sheets. This has implications for how it might be extracted. You cannot simply drill a hole and pump out water. Instead, you would need to mine the regolith, heat it to release the water as vapor, and then condense and purify the vapor. This is technologically feasible, but it requires equipment and energy. How much water is there? Estimates vary widely. The concentration in the shadowed craters might be a few percent by weight, or it might be much less. The total amount could be billions of tons, enough to supply a permanent settlement for centuries, or it could be far smaller. Characterizing these deposits accurately is essential for planning future missions. If the water is abundant and accessible, it changes everything. Rocket fuel made from lunar water would drastically reduce the cost of deep space exploration. Rather than lifting every drop of propellant from Earth's deep gravity well, spacecraft could refuel at the Moon and proceed to Mars or the asteroids with full tanks. The Moon would become a gas station, a stepping stone, a hub in a growing network of human activity in space. But water is just one resource. The lunar regolith is rich in oxygen, which is chemically bound to other elements in minerals like ilmenite, anorthite, and olivite. Extracting this oxygen requires breaking chemical bonds, which takes energy, but the oxygen is there, comprising about 45% of the mass of typical lunar soil. A facility that processes regolith could produce oxygen for breathing and for combining with hydrogen to make water, or with other elements to make rocket fuel. Metals are present too. Iron exists in the lunar soil, both in mineral form and as tiny grains of pure iron created by micrometeorite impacts and solar wind reduction. Aluminum is abundant in the highland rocks. Titanium is enriched in some mare basalts. Processing these metals on the Moon could eventually support manufacturing, reducing the need to launch everything from Earth. And then there is helium-3. The solar wind carries this light isotope and implants it in the regolith, where it accumulates over time. Helium-3 is rare on Earth, but potentially valuable as fuel for fusion reactors. The catch is that practical fusion power remains a distant goal. We have not yet achieved a sustained energy-positive fusion reaction on Earth, let alone one that uses helium-3. If fusion technology matures, lunar helium-3 could become valuable indeed. If not, it will remain a curiosity. The economics of lunar resource extraction are uncertain. Early estimates suggested that mining the Moon could be profitable, but these calculations depend on many assumptions about technology development, launch costs, and market demand. What seems clear is that using lunar resources to support lunar activities makes more sense than shipping everything from Earth. Whether lunar resources can support profitable export back to Earth is a more distant question. Regardless of economics, the scientific value of lunar resource studies is substantial. Understanding how volatiles like water cycle on an airless body helps us understand similar processes on asteroids and other moons. Developing techniques for in situ resource utilization advances engineering capabilities that will be needed wherever humans go in the solar system. The Moon serves as a laboratory for technologies and concepts that are applicable far beyond. Now, let us turn to what the Moon can tell us about the universe beyond our solar system. Because the Moon lacks an atmosphere, its surface is exposed directly to space. This means that cosmic rays, high-energy particles from distant sources like supernovae and black holes bombard the regolith continuously over billions of years. These particles leave traces in the soil, a record of the cosmic ray environment through time. By studying these traces, scientists can learn about the history of our galaxy. The Moon's lack of atmosphere also makes it an ideal platform for certain kinds of telescopes. Radio telescopes on the far side would be shielded from Earth's electromagnetic noise, able to detect faint signals that are drowned out on our planet. Of particular interest are signals from the cosmic dark ages, the period before the first stars formed when the universe was filled with neutral hydrogen. This hydrogen emitted radio waves at a specific frequency that has been stretched by the expansion of the universe to much longer wavelengths today. Detecting these signals is extremely challenging from Earth, but a radio telescope on the far side of the Moon might succeed. Optical telescopes would also benefit from the lunar environment. Without an atmosphere to blur images or scatter light, lunar telescopes could achieve extraordinary resolution. The long, stable nights would allow extremely long exposures, and the Moon's low gravity would allow the construction of larger mirrors than would be practical on Earth. Of course, building and operating telescopes on the Moon presents enormous challenges. The equipment must survive the extreme temperatures and the harsh radiation environment. Maintaining and repairing instruments would require either robotic systems sophisticated enough to handle delicate work or the presence of human technicians. The cost of building infrastructure on the Moon would be immense, but the potential rewards match the challenges. Fundamental questions about the universe, questions about the origin and nature of dark matter, the conditions in the early cosmos, the existence of other Earth-like planets might be answered by observations that are only possible from the Moon. The Moon could become not just a destination for exploration, but a platform for discovery. The scientific community has long dreamed of these possibilities. Concepts for lunar telescopes have been studied for decades. What was once speculative is becoming increasingly concrete as return to the Moon draws nearer. The Artemis program and its international partners are already considering what scientific facilities might be established on or around the Moon in the coming decades. Let us also consider what the Moon can teach us about the phenomenon of impact cratering, one of the most fundamental processes shaping solid bodies throughout the solar system. Craters form when an object strikes a surface at high speed, releasing enormous energy in an instant. The impactor is typically destroyed, and a cavity is excavated in the target material. Rock is shattered, melted, and even vaporized. Material is thrown outward to form an ejector blanket surrounding the crater. For large impacts, the crater floor may rebound upward, creating a central peak or a ring of peaks. The Moon is essentially a museum of impact craters, with examples ranging from microscopic pits in individual grains of regolith to enormous basins hundreds of kilometers across. By studying this diversity, scientists have developed a detailed understanding of how craters form and evolve, knowledge that applies not just to the Moon, but to Mercury, Mars, asteroids, and the icy moons of the outer planets. The size and morphology of a crater depend on many factors: the size and speed of the impactor, the angle of impact, the composition and structure of the target surface. Fresh craters have sharp rims and steep walls, but over time, smaller impacts gradually erode and soften these features. By examining how degraded a crater appears, scientists can estimate its relative age. The largest impacts excavate basins so big that the Moon's lithosphere cannot support their weight. The floor of the basin rebounds and later collapses in a complex process that creates multiple concentric rings, structures seen in the great multi-ring basins like Orientale and Imbrium. These basins are windows into the Moon's interior, places where deep material has been brought to the surface. Some craters preserve evidence of the impactors themselves. While most impactor material is vaporized or mixed beyond recognition with target rock, certain craters contain identifiable meteoritic material. This allows scientists to determine what kind of object caused the impact, whether a rocky asteroid, an iron-rich meteorite, or perhaps a cometary fragment. Understanding the population of impactors helps reconstruct the dynamical history of the solar system. Craters also create opportunities. Permanently shadowed craters at the poles trap water ice. Crater walls can shield habitats from radiation and temperature extremes. Crater floors provide relatively flat terrain in otherwise rugged regions. Some craters may offer access to materials from depth that would otherwise be inaccessible. As we have seen, the study of lunar craters has implications far beyond the Moon. The late heavy bombardment hypothesis, the evidence for giant impacts in Earth's history, the hazard posed by near-Earth objects today. All these topics connect to what we learn from the Moon's battered face. Every crater is a story, and the Moon has billions of them to tell. The Moon also provides a record of the Sun's history. The solar wind, a stream of charged particles flowing outward from the Sun, implants atoms into the lunar regolith. By measuring the abundances and isotopic ratios of these implanted atoms, scientists can learn about the composition and variability of the solar wind over time. Changes in solar activity might be recorded in layers of regolith, with periods of higher activity leaving different signatures than quieter times. The Sun's output affects Earth's climate and space environment, so understanding its long-term behavior is of practical as well as scientific interest. The Moon offers a 4 billion-year archive of solar activity, a record far longer than anything preserved on Earth. Solar flares and coronal mass ejections, explosive events that send bursts of energetic particles into space, are also recorded on the Moon. When these events occur, they damage the crystal structure of surface minerals in characteristic ways. Studying these radiation tracks provides information about the frequency and intensity of extreme solar events. Since such events can disrupt technology and pose hazards to astronauts, understanding their history is important for planning future activities in space. The relationship between the Moon and Sun goes deeper still. The Moon moderates the effect of solar heating on the Earth's oceans through the tides. The Moon's phases have been used for millennia to track the passage of time, complementing solar calendars. In eclipses, the Moon passes directly between Earth and Sun, briefly blocking the solar disk and allowing observers to see the Sun's corona, its outer atmosphere. Total solar eclipses have driven major scientific discoveries, including the confirmation of Einstein's general theory of relativity in 1919, when the bending of starlight by the Sun's gravity was measured during an eclipse. The Moon is perfectly sized and perfectly positioned to create total solar eclipses as viewed from Earth. This is a remarkable coincidence. The Sun is about 400 times larger than the Moon, but it is also about 400 times farther away, so they appear nearly the same size in our sky. This is not the case for any other planet in the solar system. Our Moon is unusually large relative to its planet, and the result is a celestial alignment that has inspired awe and driven scientific inquiry for centuries. But this coincidence will not last forever. As the Moon slowly recedes from Earth, it will appear smaller in the sky. Eventually, hundreds of millions of years from now, the moon will be too distant to fully cover the sun, and total solar eclipses will be a thing of the past. We are fortunate to live in an era when they still occur, a reminder of how conditions change even in the seemingly eternal heavens. The human fascination with the moon runs so deep that it has shaped languages and myths around the world. In nearly every culture that has looked up at the night sky, the moon has taken on symbolic meaning. The ancient Egyptians associated the moon with Thoth, the god of wisdom and writing. In Hindu tradition, Chandra is the lunar deity who rides a chariot drawn by antelopes across the night. The Japanese see a rabbit pounding rice cakes in the patterns of the Maria. Chinese legend tells of Chang'e, a woman who became immortal and lives on the moon with a jade rabbit. These myths are not merely quaint relics of prescientific thinking. They reveal something fundamental about the human mind, our need to find meaning and story in the world around us. The moon, ever-present and ever-changing, provided a perfect canvas for these stories. Its regular cycle from new to full and back again suggested themes of renewal and transformation. Its soft light in the darkness offered comfort and mystery in equal measure. The scientific study of the moon has not diminished this sense of wonder. If anything, knowing the truth about our companion world makes it more wondrous. The moon was born in unimaginable violence, forged from the debris of a planetary collision. It has witnessed the entire history of Earth, from the cooling of the Magma ocean to the emergence of life, to the rise of beings capable of building rockets and walking on its surface. It holds clues to questions we are only beginning to ask. And yet, for all our knowledge, so much remains unknown. We do not know the precise details of the giant impact. We do not know exactly when the moon acquired its water, or where that water came from. We do not know why volcanic activity persisted longer in some regions than others. We do not know whether the interior still harbors any significant heat, or whether it has cooled completely. We do not know what minerals might lie in the unexplored regions near the poles, or in the depths of the South Pole Aitken Basin. Each answer we find leads to new questions. That is the nature of science, and the moon exemplifies it perfectly. A world that once seemed simple, a rock orbiting Earth, has revealed layer upon layer of complexity, and we have only scratched the surface. Let us imagine for a moment what the moon might look like in the future. The Artemis program aims to establish a sustained human presence at the lunar South Pole. If that vision is realized, what might we see? Habitats clustered near the rim of a crater, positioned to receive sunlight, while maintaining access to the shadowed regions where water ice awaits. Solar panels stretching across the bright highlands, generating power that flows to extraction plants that process regolith for water, oxygen, and metals. Rovers traversing the grey landscape, some operated by humans in spacesuits, and others moving autonomously on pre-programmed routes. A communication relay perched on a high point, maintaining contact with Earth and with orbital facilities. Inside the habitats, life would be strange, but increasingly routine. Astronauts would sleep in quarters pressurized with air recycled hundreds of times. They would eat food grown in hydroponic gardens supplemented by supplies from Earth. They would exercise daily to maintain bone and muscle in the weak gravity. They would conduct research, maintain equipment, and venture outside in spacesuits that have evolved far beyond those worn by the Apollo astronauts. The first inhabitants would be explorers and scientists, people driven by curiosity and a sense of mission. But over time, the population might diversify. Engineers would arrive to build and maintain infrastructure. Technicians would operate the resource extraction equipment. Perhaps eventually tourists would visit, spending a few days or weeks experiencing a place utterly unlike anywhere on Earth. This is speculative, of course. Many challenges must be overcome before any of this becomes reality. The cost of establishing a permanent base would be enormous. The risks to human health from radiation, reduced gravity, and isolation are not fully understood. The political will to sustain such an effort over decades cannot be taken for granted. But the trajectory is clear. The Moon is no longer a place we merely visit. It is becoming a place we intend to use. The resources it offers, the scientific opportunities it presents, the strategic advantages it may confer, all point toward a future where humans live and work on the Moon as a matter of course. What would it feel like to live there? The silence would be the first thing you notice. Without an atmosphere, there is no sound outside the habitat. The landscape is utterly still. No wind rustling, no birds calling, no distant traffic. Only the creaking of your spacesuit and the sound of your own breathing. The sky is black even during the day, with stars visible above the horizon. Earth hangs in that sky, a brilliant blue and white sphere, the only color in a monochrome world. The light is harsh and unfiltered. Shadows are sharp and deep, with no diffusion to soften edges. The temperature swings are extreme, but inside your suit or habitat, you are shielded from them. The gravity is about 1/6 of Earth's, weak enough that you could jump several meters high, strong enough that walking feels familiar if bouncy. The landscape itself is ancient and unchanged. The hills on the horizon look the same as they did 1 billion years ago. The craters that dot the surface will look the same 1 billion years hence. There is a strange comfort in this permanence, a sense of standing in deep time. But there is also isolation. Earth is only 3 days away by spacecraft, but communication delays are minimal, measured in seconds. Still, the psychological distance is immense. Everything you know, everyone you love, exists on that small bright disk in the sky. The Moon is a world apart. Astronauts who have been to space often speak of a shift in perspective. Seeing Earth from outside, recognizing it as a single fragile system in the vast darkness, changes how you think about borders and conflicts and the future of our species. This overview effect, as it is sometimes called, might be amplified for those who spend extended time on the Moon. They would have daily reminders of Earth's isolation and beauty. Such experiences could influence how we approach the challenges facing our home planet, climate change, resource depletion, conflict over territory. All might seem less intractable when viewed from a place where the entire Earth fits within your gaze. This is not to say that space exploration will solve Earth's problems, but it offers a vantage point from which those problems can be seen more clearly. The Moon could also serve as a backup of sorts if some catastrophe befell Earth, whether a natural disaster like a supervolcano or an asteroid impact, or a human-caused calamity like nuclear war or engineered pandemic. A self-sustaining lunar settlement might preserve human civilization. This is an extreme scenario, and no one advocates for space colonization primarily as insurance against extinction. But it is worth noting that spreading beyond a single world reduces existential risk. More immediately, the Moon offers opportunities for international cooperation. Space exploration has often brought nations together, from the Apollo-Soyuz mission during the Cold War to the International Space Station partnership today. The Artemis program includes agreements with multiple countries. building a framework for shared governance of lunar activities. If nations can work together on the Moon, perhaps they can find common ground on Earth as well. Of course, space can also become a domain of competition and conflict. Access to resources, strategic positions, and national prestige could drive rivalry rather than cooperation. The legal frameworks governing space activities, established in the 1960s and 1970s, may prove inadequate for a future of commercial mining and permanent settlements. How we navigate these challenges will shape not just lunar development, but the broader trajectory of human civilization. Let us return to the science and consider what remains to be discovered. The Moon's internal structure is still imperfectly known. The Apollo seismometers provided foundational data, but they operated for less than a decade and were positioned in a limited area. A global seismic network with modern instruments could reveal the details of the core, mantle, and crust with far greater precision. This would help us understand how the Moon differentiated and cooled, processes that occurred on all rocky worlds. The magnetism of the Moon presents puzzles. Ancient lunar rocks show evidence of a magnetic field that was surprisingly strong, comparable to Earth's field today. But the Moon's small iron core should not have generated such a strong field through a conventional dynamo mechanism. Either our understanding of dynamos is incomplete, or some other process was at work. Proposed explanations include mechanical stirring of the core by large impacts, unusual convection patterns driven by crystallization, or interactions with the Moon's ancient orbital dynamics. Resolving this mystery would have implications for understanding magnetic field generation on other worlds. The composition of the lunar interior remains uncertain. We know the surface rocks well, at least in the regions that have been sampled, but deeper materials are harder to access. The South Pole Aitken Basin may have excavated mantle rocks, and samples from this region could provide direct evidence of what lies beneath the crust. Understanding the mantle's composition would constrain theories of lunar formation and early evolution. Volatile elements on the Moon are not limited to water. Carbon compounds, nitrogen, sulfur, and noble gases have all been detected in various forms. Understanding the abundances and distributions of these volatiles would illuminate the processes that delivered and retained them. Were they primarily brought by comets? By certain types of asteroids? Were they outgassed from the interior? Each source leaves different fingerprints. The history of impacts can be read in greater detail with more samples and better crater counts. Are there distinct spikes in the impact rate, like the proposed late heavy bombardment? Did the flux decline smoothly over time? Has it remained roughly constant for the past 3 billion years? Answering these questions has implications for understanding the hazard posed by asteroids and comets to Earth today. The relationship between the Moon and biological evolution on Earth is another area ripe for investigation. We know tides influence coastal ecosystems, but quantifying these effects over deep time is challenging. The stabilization of Earth's axial tilt by the Moon likely helped maintain a relatively stable climate, but how important was this for the emergence and persistence of complex life? These are difficult questions to answer definitively, but they highlight the deep connections between our world and its companion. The scientific potential of the Moon extends beyond studying the Moon itself. As a stable platform with no atmosphere, it offers unique advantages for observatories. Low-frequency radio astronomy could finally observe the cosmic dark ages. Optical and infrared telescopes could achieve resolutions impossible on Earth. Gravitational wave detectors might operate with reduced noise. the Moon could become a hub for astronomical research, a permanent outpost for exploring the universe. And as a waypoint for deeper exploration, the Moon's value is strategic as well as scientific. Fuel produced on the Moon could dramatically reduce the cost of missions to Mars, the asteroids, and beyond. A base on the Moon would provide experience and technology development that transfers to more distant destinations. The Moon is not the final frontier, but it is the first real step beyond our home world. Consider Mars, that rust-colored world that has captivated human imagination for centuries. Reaching Mars is vastly more difficult than reaching the Moon. The journey takes months rather than days. Communication delays are measured in minutes rather than seconds. The resources of Earth cannot quickly respond to emergencies. Living on Mars would require self-sufficiency to a degree that the Moon does not demand. Yet everything we learn on the Moon applies to Mars. Life support systems, radiation protection, habitat construction, resource extraction, psychological resilience, all these challenges exist on the Moon and would be amplified on Mars. By solving them first on the Moon, we prepare for the greater leap. The Moon also serves as a proving ground for international cooperation in space. The Artemis Accords, a set of principles for peaceful and transparent lunar exploration, have been signed by numerous countries. These agreements establish norms for how nations and companies should behave on the Moon, respecting each other's operations, sharing scientific data, avoiding harmful contamination. Whether these norms will hold as commercial interests grow remains to be seen, but the effort to establish them is significant. Historically, new frontiers have often been contested. The exploration and colonization of Earth's continents brought conflict, exploitation, and tragedy alongside discovery and achievement. Space need not follow the same pattern. The unique conditions of space, the hostility of the environment, the necessity of cooperation for survival, the shared heritage of humankind in outer space enshrined in treaty, these offer hope for a different outcome. But hope is not enough. Deliberate effort is required to ensure that lunar development benefits all of humanity, not just a few nations or corporations. Questions of governance, resource rights, environmental protection, and inclusion must be addressed before problems become entrenched. The decisions made in the coming decades will shape the human presence on the Moon for centuries. These are weighty matters, and they may seem far removed from the quiet wonder of gazing up at the Moon on a clear night. But they are connected. The same impulse that drove ancient humans to ponder the Moon's nature drives us to explore it, to understand it, to use it wisely. We are continuing a story that began when the first person looked up and asked what that light might be. And so, the Moon remains what it has always been, a mirror for human aspirations, a record of cosmic history, a destination calling us outward. Its face, so familiar and yet so alien, looks down on generation after generation, unchanging while we grow and strive and dream. It waited patiently while we invented fire, writing, telescopes, rockets. It will wait still as we return, as we build, as we reach for yet more distant shores. The story of lunar science is a story of questions and answers, each answer leading to new questions. We have learned that the Moon was born in fire, shaped by impacts, frozen in time. We have learned that it holds water in its coldest craters and ancient history in its oldest rocks. We have learned that it stabilizes our world and marks our time. And we have learned that it is within our reach, a place we can visit and perhaps one day call home. But we have not learned everything. The Moon still holds secrets, and that is perhaps the most wonderful thing of all. Let us journey back in time now to imagine what the Moon was like in its earliest days. 4.5 billion years ago, the solar system was a dangerous place. The Sun had recently ignited, blowing away much of the gas and dust from which it had formed. Rocky debris swirled in orbit, colliding and combining to build the planets. Earth was young, perhaps only 100 million years old, when catastrophe struck. A body roughly the size of Mars came hurtling toward our infant planet. We call this impact a Theia, after the mythological mother of the moon goddess Selene. The collision was not a glancing blow that might have sent both bodies tumbling apart. It was a direct, violent impact that released energy almost beyond comprehension. In an instant, tremendous heat was generated. Rock vaporized. The outer layers of both Earth and Theia were blasted into space. A disk of debris, a mixture of molten rock and gas, swirled around the wounded Earth. This disk was hot, so hot that some material escaped to space while the rest gradually cooled and began to clump together under its own gravity. Within perhaps 100 years, an astonishingly short time in cosmic terms, the debris had coalesced into a new body, the Moon. It orbited much closer to Earth than it does today, perhaps 10 times closer. It would have loomed enormous in the sky, filling much of the view for any eyes that might have looked up. But there were no eyes, yet. Life would not emerge for another several 100 million years. The newborn Moon was hot, likely covered by a magma ocean hundreds of kilometers deep. As this ocean cooled, crystals formed and began to settle or float depending on their density. Light minerals, particularly a type of feldspar called anorthite, floated to the surface, forming a crust of bright highland rock. Denser minerals sank to form the mantle. The heaviest elements, mostly iron, collected at the center to form a small core. This process of differentiation, the separation of a planetary body into layers of different composition, happened relatively quickly. Within a few 100 million years, the Moon had acquired the basic structure it retains today: a solid crust, a rocky mantle, and a small metallic core. But the universe was not done shaping the Moon. The early solar system was crowded with debris, the leftover building blocks of planet formation. These objects, ranging from dust grains to bodies hundreds of kilometers across, bombarded the young Moon relentlessly. Each impact scarred the surface, excavating craters and mixing the regolith. The largest impacts created basins hundreds of kilometers in diameter. The shock waves from these collisions fractured rock deep beneath the surface. The heat generated by the impacts may have remelted portions of the crust, and the debris ejected from each crater spread across the Moon, forming layers of material that geologists can identify and date. Some of these ancient basins are still visible today as vast circular features, their original sharp rims softened by billions of years of subsequent impacts. The South Pole Aitken Basin, on the far side, is the largest and perhaps the oldest, a scar more than 2,000 kilometers across and several kilometers deep. The Imbrium Basin, on the near side, is younger but still ancient, formed about 3.9 billion years ago in an impact that spread debris across much of the lunar surface. The rain of debris gradually slackened as the solar system cleared out its leftover material. By about 3.8 billion years ago, the worst of the bombardment was over. The Moon's surface, now cold and rigid, began its long slumber, disturbed only by occasional impacts and, for a time, volcanic eruptions. The volcanic era of the Moon began after the crust had solidified. Deep beneath the surface, radioactive elements like uranium, thorium, and potassium decayed, generating heat. This heat accumulated over time, eventually melting rock in the upper mantle. The magma, less dense than the solid rock around it, rose toward the surface. On Earth, such magma often erupts explosively through volcanoes, driven by dissolved gases that expand violently as pressure drops. But the Moon has no atmosphere to contain these gases. When lunar magma reached the surface, gases escaped immediately into the vacuum of space, producing eruptions that were more like floods than explosions. Lava poured across the landscape in vast sheets, pooling in the low-lying impact basins. These lava flows created the maria, the dark patches that give the Moon its familiar face. The maria are not seas of water, but seas of solidified basalt, a volcanic rock rich in iron and magnesium. They are darker than the highlands because basalt absorbs more light than the feldspar-rich highland rocks. The eruptions were not continuous. They occurred in episodes, likely triggered by pulses of heat from the interior or by the triggering effects of large impacts. Different lava flows in the same basin can have measurably different ages and compositions, indicating that the volcanic history was complex. The youngest mare basalts are about 3 billion years old, and perhaps some are even younger, as the recent Chang'e 5 samples suggest. But most volcanic activity ended long ago. The Moon, smaller than Earth and with less radioactive material, could not maintain the internal heat needed for volcanism. Its interior cooled, solidified, and fell silent. Or mostly silent. The Moon still experiences seismic activity, as we discussed earlier. Deep moonquakes, triggered by tidal stresses, rumble through the interior. Shallow moonquakes, their cause still debated, occasionally shake the crust. These events are far weaker than terrestrial earthquakes, but they remind us that the Moon is not entirely dead. There may even be remnants of volcanic activity in recent geological time. Some images show features that resemble volcanic vents or lava flows that appear remarkably fresh. These irregular mare patches, as they are called, could be only tens of millions of years old, practically yesterday in geological terms. If the Moon was still erupting so recently, it would suggest that the interior retains more heat than previously thought. Confirming or refuting this possibility is a goal for future missions. The timeline we have constructed for the Moon, from fiery birth to cold quiescence, is remarkably detailed considering that humans have only been visiting for a little over 50 years. But gaps remain. The period between the Moon's formation and the oldest rocks we have sampled, roughly the first 400 million years, remains poorly understood. Rocks from this era, if they survive at all, would be incredibly valuable. The far side of the Moon is especially understudied. Nearly all Apollo samples came from the near side, from landing sites chosen partly for safety and communication reasons. The far side, with its different terrain and potentially different history, awaits systematic exploration. Samples from the far side highlands, from the floor of the South Pole Aitken Basin, and from the polar regions could revolutionize our understanding. The polar regions are of particular interest because they may preserve materials that have been destroyed elsewhere. The extremely cold temperatures in permanently shadowed craters would prevent the loss of volatile compounds that would evaporate in sunlight. If ancient comets delivered organic molecules to the Moon, traces might survive in these cold traps. Such materials could provide clues about the delivery of prebiotic chemicals throughout the early solar system. Similarly, the lunar surface may preserve tiny fragments of early Earth. Large impacts on our planet would have ejected rocks into space, some of which might have landed on the Moon. On Earth, rocks from 4 billion years ago are exceedingly rare because geological processes have recycled most ancient material. But on the Moon, without plate tectonics or erosion, these fragments might remain intact, waiting to be found. Discovering a piece of the early Earth on the Moon would be an extraordinary achievement. The search for such materials requires sophisticated techniques for distinguishing lunar from non-lunar rocks. Isotopic analysis, which examines the ratios of different forms of the same element, can reveal a rock's origin. Earth rocks have distinctive isotopic signatures that would stand out against the lunar background. The work is painstaking, like searching for a needle in a haystack, but the potential reward justifies the effort. Let us consider now the future of lunar science and exploration in more concrete terms. The Artemis program has set ambitious goals. The first crewed landing, designated Artemis 3, will place astronauts near the lunar South Pole, a region never before visited by humans. They will conduct experiments, collect samples, and demonstrate technologies for longer stays. Subsequent missions will expand the explored area and increase the duration of surface operations. Central to the Artemis vision is the Gateway, a small space station that will orbit the Moon. Unlike the International Space Station, which orbits Earth at a relatively low altitude, Gateway will follow a highly elliptical path that brings it close to the Moon at some points and farther away at others. This orbit uses minimal fuel to maintain and provides access to different lunar regions. Gateway will serve as a staging point for surface missions. Astronauts will travel from Earth to Gateway in the Orion spacecraft, then transfer to a lunar lander for the descent to the surface. After their stay on the Moon, they will return to Gateway and, eventually, to Earth. This architecture allows for longer and more complex surface missions than would be possible with a direct Earth-to-Moon-to-Earth approach. The station will also host scientific instruments and serve as a platform for research that benefits from the deep space environment. Studies of cosmic rays, solar wind, and the space radiation environment will inform plans for missions to Mars and beyond. Telescopes and other remote sensing instruments may observe the Moon, Earth, and the broader universe from Gateway's unique vantage point. International partners are integral to Artemis. The European Space Agency is contributing modules to Gateway. Japan is developing life support systems. Canada is providing a robotic arm. Other nations have signed the Artemis Accords and may contribute to future missions. This collaboration distributes costs and expertise while building relationships that extend beyond space exploration. Commercial companies are also essential partners. NASA has contracted with private firms to develop human landing systems, with the goal of fostering a competitive market that drives down costs and spurs innovation. Robotic landers developed by commercial providers will deliver science payloads and technology demonstrations before crewed missions arrive. This public-private partnership represents a new model for space exploration, different from the government-led approach of Apollo. The pace of progress depends on many factors: technical challenges, funding decisions, political priorities, and unforeseen events. Schedules have slipped and will likely slip again, but the direction is set. Humans will return to the Moon, and this time we intend to stay. What science will they do? Sample collection remains a priority. Rocks from the South Polar region will provide new data about the Moon's composition and history. Ice from permanently shadowed craters will be analyzed to determine its origin and abundance. Materials that might have been delivered by comets or ejected from early Earth will be searched for systematically. Seismology will be advanced by deploying new networks of sensors. The Apollo seismometers operated for years, but they covered only a small area on the near side. A global network, including stations on the far side and at the poles, would dramatically improve our understanding of the lunar interior. Such a network might be deployed robotically, with astronauts visiting to maintain and upgrade the stations as needed. Astronomy will take its first steps on the lunar surface. Small telescopes and radio antennas will test the feasibility of larger facilities. If these pathfinders succeed, they could pave the way for major observatories that exploit the Moon's unique environment. Radio telescopes on the far side, shielded from Earth's interference, might detect signals from the cosmic dark ages that are invisible from anywhere else. Biology experiments will explore how organisms respond to the lunar environment. The weak gravity, the radiation, the isolation, all pose challenges and opportunities. Understanding how plants grow in lunar conditions could inform plans for sustainable food production. Studying how microbes survive could reveal strategies for protecting astronauts from contamination, or for using organisms to process resources. Technology demonstrations will test systems needed for long-term presence, extracting water from regolith, producing oxygen from minerals, manufacturing construction materials, generating power during the long lunar night. All these capabilities must be proven before permanent settlements become feasible. Each mission will advance the state of the art, learning from successes and failures alike, and there will be exploration for its own sake. Astronauts will travel to places no human has seen up close. They will photograph landscapes of stark beauty. They will stand at the rims of ancient craters and peer into depths that have been dark for billions of years. They will experience the silence and the stillness and the profound isolation of a world without air. These experiences will be shared with people on Earth in ways that Apollo could not achieve. High-definition video will stream in real time. Virtual reality experiences will let viewers feel as if they are standing beside the astronauts. The sense of shared adventure, of participating in a great human endeavor, could inspire generations. Inspiration matters. The Apollo missions captivated the world and motivated countless young people to pursue careers in science, engineering, and exploration. That legacy continues today, decades after the last astronauts left the Moon. The return to the Moon could have a similar effect, perhaps even greater given the ability of modern communications to reach every corner of the planet. But inspiration must be sustained by substance. The science must be real. The technology must advance. The benefits must flow back to society. Otherwise, interest will fade and support will wane. The architects of Artemis understand this, which is why the program emphasizes sustainability. Not just landing and leaving, but building capabilities that endure. Though Moon is close enough to reach, but far enough to challenge us. It is familiar enough to feel like a destination, yet alien enough to teach us new things. It offers resources that could support exploration deeper into the solar system and scientific opportunities unavailable anywhere else. And it connects us to our past, to the generations of humans who looked up in wonder and asked what that light in the sky might be. We are the inheritors of that long tradition of curiosity. We stand on the shoulders of Galileo and the Apollo astronauts and all who came between and after. And we look forward to a future in which the Moon is not just a destination, but a home, a place where humans live and work and dream of yet more distant shores. The night sky has always been a gateway to wonder. From the earliest cave dwellers who painted the stars on rock walls To the modern astronomers who peer through sophisticated telescopes, humans have sought to understand our place in the cosmos. The moon has been our constant companion in this journey, the nearest step beyond our home world, the first destination we reached when we finally learned to fly. But reaching the moon was not the end of the story. It was a beginning. The samples brought back by Apollo transformed our understanding of planetary science. The instruments left behind continued to send data for years. And the experience of standing on another world changed forever how we think about exploration. Now we stand at another beginning. The technology that made Apollo possible has evolved dramatically. Computers that once filled buildings now fit in our pockets. Materials that did not exist in the 1960s now provide lighter, stronger, more durable components. Communications that were limited to audio and grainy video can now stream high-definition images across the solar system. These advances mean that the return to the moon will be different from the first visits. More can be accomplished with less. Longer stays are feasible. Greater scientific return is possible. The dreams of permanent presence that seem far-fetched after Apollo now appear within reach. Consider the advances in robotics. The rovers and landers of the early space age were simple by modern standards. Today's robots can navigate autonomously, make decisions based on sensor data, and conduct experiments with minimal human intervention. A new generation of lunar robots could prepare the way for human explorers, mapping terrain, prospecting for resources, and even beginning to construct habitats before the first astronauts arrive. Such precursor missions are already planned. Small landers developed by commercial companies will deliver payloads to the lunar surface, testing technologies and gathering data. Rovers will explore promising sites near the South Pole. Drills will sample the regolith to determine water content. Each mission builds knowledge and reduces risk for the crewed expeditions that follow. The synergy between robotic and human exploration is one of the great lessons of the space age. Robots can go places too dangerous or expensive for humans. They can operate for years without rest or resupply. But humans bring judgment, adaptability, and the ability to respond to unexpected discoveries. The most effective exploration strategy combines both, with robots scouting ahead and humans following to do what robots cannot. This partnership will extend to the moon's surface. Astronauts will command rovers to retrieve samples from distant locations. Robots will assist with construction and maintenance tasks. The line between human and robotic exploration will blur as both work together toward common goals. The question of what drives this exploration is worth considering. National prestige motivated much of the space race, but today's motivations are more diverse. Scientific curiosity remains paramount, the desire to understand the universe and our place in it. Commercial interests have emerged, with companies seeing opportunities in launch services, resource extraction, and space tourism. Strategic considerations play a role, as nations seek to ensure their access to space and their influence over how space is governed. And there is the simple human impulse to explore, to see what lies beyond the horizon, to test the limits of what is possible. All these motivations converge on the moon. It is scientifically rich, commercially promising, strategically significant, and endlessly fascinating. It is close enough to reach, but challenging enough to push technology forward. It is a world in its own right, and a stepping stone to others. The stepping stone function deserves emphasis. Mars has long been the dream destination for many space enthusiasts, a world with a day almost as long as Earth's, with seasons, with ice caps and ancient riverbeds, Mars seems like a place where humans could someday live. But reaching Mars is immensely harder than reaching the Moon. The journey takes months, not days. The return requires launching from Mars's surface, a feat that has never been accomplished. The communication delays make real-time control from Earth impossible. Everything we learn on the Moon prepares us for Mars. The technologies for extracting water and oxygen, for constructing habitats, for protecting against radiation, for living in reduced gravity, all must be developed and tested somewhere. The Moon is that somewhere. It is close enough that problems can be addressed quickly, but harsh enough that solutions must be robust. Some have argued that the Moon is a distraction, that we should focus directly on Mars and not waste time on a destination we have already reached. But this view misunderstands the nature of exploration. Apollo was a sprint, a race to be first. What comes next must be a marathon, building sustainable capabilities that can be maintained and expanded over decades. The Moon is where we learn to do that, and the Moon has its own value, independent of Mars. The scientific questions are real and important. The resources are real and potentially valuable. The experience of living on another world is something humanity has never truly had. Apollo gave us glimpses, but those glimpses were brief, measured in hours. What we learn from extended stays will be qualitatively different. Consider the challenge of lunar dust. The fine particles that cover the Moon's surface are sharp and abrasive, not worn smooth by wind and water as on Earth. They cling to everything, worked into fabrics and seals by electrostatic forces. Apollo astronauts found the dust annoying and potentially hazardous, getting into equipment and lungs. Managing dust will be essential for long-term operations, requiring innovations in materials, filtration, and cleaning techniques. Consider the challenge of power during the lunar night. The sun provides abundant energy during the 2-week day, but it disappears entirely during the 2-week night. Solar panels alone cannot sustain a Yebei base through this long darkness. Options include energy storage systems such as batteries or fuel cells, nuclear power sources, or locating bases at the poles where some areas receive nearly continuous sunlight. Each approach has advantages and challenges. Solving this problem on the Moon teaches lessons applicable wherever humans go in the solar system. Consider the psychological challenges of isolation and confinement. Astronauts on the International Space Station are relatively close to Earth, with communication delays measured in fractions of a second and the possibility of emergency return. Lunar inhabitants will be farther away, and Mars inhabitants farther still. Understanding how people cope with long-term separation from home, how they maintain mental health and team cohesion, how they handle the stress of living in a dangerous environment, these are questions that must be answered before we venture farther. The Moon is our laboratory for answering them. Every challenge we face there, every solution we develop, advances our capability for exploration beyond. Now let us look even farther ahead and imagine what the Moon might mean for humanity a century or more from now. If current trends continue, the 22nd century could see a permanent human presence on the Moon, not just a research base visited by rotating crews, but a genuine settlement with families, schools, businesses, and all the complexity of human society. This is speculative, of course. Many things could prevent such a future or delay it far beyond what optimists predict, but it is worth imagining. A lunar settlement would be unlike any community on Earth. The environment would impose constraints that shape every aspect of life. Homes would be pressurized habitats, perhaps underground, to provide protection from radiation and temperature extremes. Moving between buildings would require spacesuits or pressurized vehicles or connected tunnels. Activities that we take for granted, like stepping outside for fresh air, would be impossible. Yet humans are remarkably adaptable. We have lived in deserts and Arctic tundras, on isolated islands and in dense cities. We have created cultures suited to every environment Earth offers. We would do the same on the Moon. Over generations, a distinctly lunar culture might emerge, with its own traditions, its own art, its own ways of understanding the world. Children born on the Moon would grow up in low gravity. Their bodies might develop differently from those of Earth-born humans. They might find it difficult to visit Earth, where the six-fold stronger gravity would feel crushing. They would look up at Earth in the sky and think of it as a beautiful but foreign place, much as we think of the Moon today. This raises profound questions about human identity and destiny. If we spread to other worlds, do we remain one species, or do we diverge? What responsibilities do lunar settlers have to Earth, and what does Earth owe them? How do we ensure that the benefits and risks of space settlement are shared fairly? These questions are not merely philosophical. They have practical implications for how we govern space activities today. The choices made in the coming decades about property rights, resource allocation, environmental protection, and political representation will shape the future of human civilization in space. Some frameworks already exist. The Outer Space Treaty of 1967 declares that space is the province of all humanity and prohibits national appropriation of celestial bodies. But the treaty was written before commercial space activities were contemplated at scale, and its provisions are subject to interpretation. The Moon Agreement of 1979 attempted to establish a more detailed framework, but was rejected by the major spacefaring nations. The Artemis Accords represent a newer approach, but they have not achieved universal acceptance. Crafting governance arrangements that balance competing interests while promoting peaceful and sustainable development is one of the great challenges facing the space community. The stakes are high. Done well, space could become a domain of cooperation and shared benefit. Done poorly, it could become another arena for conflict and exploitation. The Moon, as the most accessible destination beyond Earth, will be the first test case. How we handle lunar development will set precedents for Mars, the asteroids, and whatever lies beyond. The decisions made by this generation will echo through centuries. Let us return now to the present and consider the lived experience of those who have seen the Moon up close. Only 24 humans have traveled to the Moon, all of them American astronauts on Apollo missions between 1968 and 1972. Of those 24, 12 walked on the surface. Their testimonies provide a window into what it means to stand on another world. The view of Earth from the Moon is uniformly described as transformative. That small, fragile sphere, hanging in the darkness, holds everything that matters to us. All of human history, all of art and science and love and war, all of it confined to that blue and white marble. The astronauts who saw this view returned with a new perspective on global challenges and a conviction that national borders seem arbitrary. From space, the lunar surface itself evokes different responses. Some astronauts spoke of its stark beauty, the interplay of light and shadow, the ancient craters stretching to the horizon. Others emphasized the sense of desolation, the absolute silence, the awareness of being utterly alone in a hostile environment. All struggled to find words adequate to the experience. The physical sensation of reduced gravity delighted most astronauts. Moving in 1/6 Earth gravity is like being perpetually buoyant. Each step covers more ground. Jumping is effortless, but the bulky spacesuits limited mobility, and the fine dust made footing uncertain. Astronauts learned to hop rather than walk, a distinctive gait that conserved energy and reduced the risk of falling. Working in spacesuits was exhausting. The gloves were stiff, making fine manipulation difficult. The suits were pressurized, so every movement required effort against the internal pressure. Visibility was limited by the helmet. Despite these challenges, the astronauts accomplished remarkable feats, deploying instruments, collecting samples, even driving a rover across the landscape. The experience of returning to Earth was profound. After the drama of launch, the journey, the landing, and the exploration, the return was a kind of rebirth. Astronauts emerged from their quarantine periods to a world that seemed different, or perhaps they were different. Many dedicated the rest of their lives to advocating for space exploration, environmental protection, or global cooperation. These experiences belong to a small and dwindling group. Most of the Apollo astronauts have passed away. Only a handful remain to share their memories directly, but their stories survive, recorded in interviews and memoirs, waiting to inspire future explorers. The next generation of lunar explorers will have their own experiences to share. They will see sights that no Apollo astronaut saw, exploring the polar regions and perhaps the far side. They will stay longer, learning what it means to live rather than just visit. They will face challenges their predecessors could not have imagined and overcome them with tools and techniques not yet invented. And they will carry with them the legacy of those who came before. The 12 who walked on the moon and the 12 who orbited above them opened a door that can never be closed. We know now that humans can go there. The only question is whether we will. The answer, increasingly, appears to be yes. Despite setbacks and delays, despite budget pressures and shifting priorities, the momentum toward returning to the moon continues to build. Multiple nations are engaged. Commercial companies are investing. Scientific communities are planning experiments. Young people are training for careers in space. The infrastructure of lunar exploration is taking shape. There will be disappointments along the way. Schedules will slip. Missions will fail. Budgets will be cut. The path forward will not be straight, but the direction is clear. Humanity is going back to the moon, and this time we intend to stay. What does this mean for you, watching this video, listening to these words? It means that you are living through a pivotal moment in history. The decisions being made now will determine whether humanity becomes a multiplanetary species or remains confined to Earth. The technologies being developed will shape not just space exploration, but life on our home planet. The questions being asked about governance, resources, and cooperation will define the future of civilization. You can participate in this moment. You can follow the progress of lunar missions and share in their discoveries. You can support space programs through your voice and your vote. You can pursue careers in science, engineering, or the many fields that support space exploration. You can teach the next generation to look up at the night sky and wonder. The moon has been with us since the beginning of human history. It has marked our time, inspired our stories, and guided our way. Now it offers something new, a destination, a resource, a stepping stone. The ancient companion that has watched over us for billions of years is waiting for us to return, and return we shall, not as brief visitors, but as inhabitants, not as representatives of one nation, but as emissaries of all humanity. Not to plant, flags and leave footprints, but to build homes and raise children. The moon, that familiar face in the night sky, will become a second home. This is the story of lunar science, from the first wanderings of ancient stargazers to the planned expeditions of the coming years. It is a story of questions and answers, of challenges and triumphs, of imagination and determination. It is a story that is still being written, and you are part of it. The future of lunar exploration holds possibilities that would have seemed impossible just a few decades ago. Let us explore some of these possibilities now, imagining what the moon might offer in the years and centuries to come. One of the most ambitious visions involves transforming the moon into an industrial outpost. The raw materials are there. Oxygen bound in minerals, metals like iron and aluminum, perhaps water ice in the polar shadows. The energy is there too, in the form of nearly constant sunlight at certain polar locations. What remains is to develop the technologies and build the infrastructure to harness these resources. Imagine factories on the moon, producing oxygen for breathing and propellant for rockets. Imagine refineries extracting metals from the regolith and shaping them into structural components. Imagine 3D printers building habitats from lunar materials layer by layer, without needing to lift heavy structures from Earth. This vision of in-situ resource utilization could fundamentally change the economics of space exploration. Today, every kilogram launched from Earth costs thousands of dollars. The tyranny of the rocket equation means that most of the mass of a spacecraft is propellant, leaving only a fraction for useful payload. But if propellant can be produced on the moon, spacecraft leaving lunar orbit need not carry fuel for the entire journey. They can launch light and refuel in space. This changes everything. Missions to Mars become less expensive because the heavy propellant for the return trip does not have to be lifted from Earth. Missions to the asteroids, where valuable resources may await, become more feasible. The entire solar system opens up when the moon becomes a way station rather than a destination. Such a future is not guaranteed. The technical challenges are formidable. The economics are uncertain. The political will must be sustained across decades. But the vision is compelling enough that serious people are working to make it real. Beyond industry, the moon offers unparalleled opportunities for scientific research. We have touched on many of these throughout this narrative. The study of lunar geology, the analysis of impact cratering, the investigation of water and other volatiles, the deployment of astronomical observatories. Let us now consider some of the more exotic possibilities. The moon could host experiments in fundamental physics that are impossible on Earth. The stable platform, the vacuum environment, the low seismic noise, and the absence of atmospheric interference create conditions ideal for precision measurements. Gravitational wave detectors, which on Earth must contend with vibrations from traffic and weather and tectonic activity, could achieve extraordinary sensitivity on the moon. Experiments testing the equivalence principle, searching for variations in fundamental constants, or probing the nature of dark matter might find the lunar environment uniquely suited to their needs. The far side of the moon is particularly valuable for certain observations. Shielded from Earth's electromagnetic emissions, it is the quietest place in the inner solar system for radio astronomy. Signals that are drowned out by our planet's technological chatter might be detectable there. Of special interest are the faint whispers of the cosmic dawn, the era when the first stars ignited and began to transform the universe. These signals, stretched to long wavelengths by the expansion of space, could reveal how galaxies formed and evolved, answering questions about our cosmic origins. Building radio telescopes on the far side presents obvious challenges. Communication with Earth requires relay satellites, since direct signals cannot reach our planet from that hidden hemisphere. Construction would require either robotic assembly or crewed expeditions far from any established base. Power systems would need to function through the long lunar night. Yet the scientific payoff could be immense, justifying the investment. Optical and infrared astronomy would also benefit from the lunar environment. Without an atmosphere to absorb or distort light, telescopes could observe at wavelengths blocked from Earth's surface. The long, stable nights would allow exposures impossible under terrestrial skies. And the ability to build larger mirrors in low gravity could push the boundaries of what we can see. Such telescopes might search for biosignatures in the atmospheres of exoplanets, looking for signs of life around distant stars. They might observe the earliest galaxies, formed when the universe was young. They might detect objects in our own solar system, too faint to see from Earth. The Moon could become humanity's window on the universe, a platform from which we glimpse the full grandeur of creation. The biological sciences would also find opportunities on the Moon. How do organisms respond to reduced gravity over extended periods? The International Space Station has provided valuable data on microgravity, but the Moon's 1/6 gravity represents a different regime. Understanding how plants grow, how microbes behave, how human physiology adapts to lunar conditions is essential for planning permanent settlements. Experiments might reveal whether reproduction is possible in low gravity, a question with profound implications for any species hoping to establish itself beyond Earth. The development of embryos, the formation of tissues, the processes of healing and aging, all might differ under lunar conditions. These are not merely academic questions. If humans are to live on the Moon for generations, we must understand how our bodies will respond. Medicine on the Moon will face unique challenges. The medical facilities will be limited. Evacuation to Earth in an emergency will take days rather than hours. Doctors will need to diagnose and treat conditions without the vast infrastructure of terrestrial hospitals. Telemedicine can help, but communication delays and the impossibility of physical examination from Earth impose limits. These challenges will drive innovation. Diagnostic tools will become more compact and capable. Treatment protocols will be developed for resource-limited settings. Perhaps artificial intelligence will assist with diagnosis and treatment planning, compensating for the distance from specialized expertise. The medical advances developed for lunar explorers could benefit people on Earth as well, particularly in remote or underserved areas. The psychology of lunar living deserves attention too. Isolation, confinement, and distance from home impose stresses that few on Earth experience. The small communities of lunar inhabitants will need to maintain cohesion and morale over months and years. Conflicts that might seem minor on Earth could become serious in a habitat where escape is impossible. Understanding these dynamics and developing strategies to manage them is part of the work that must be done before permanent settlements become reality. The lessons learned could have applications beyond space exploration, informing how we design communities and support mental health in challenging environments anywhere. Let us pause now and consider the deeper meaning of what we have discussed. The Moon is not just a scientific target or an industrial resource or a stepping stone to other worlds. It is a symbol, perhaps the most powerful symbol in human culture. For as long as our species has existed, we have looked up at that silvery disk and wondered. It has represented mystery, beauty, change, constancy, aspiration, and romance. It has been woven into every mythology and every poetry. It has marked the rhythm of our lives. When humans walked on the moon in 1969, something changed in our relationship with that ancient symbol. The moon was no longer merely an object of wonder. It became a place, a destination, somewhere we had actually been. The mythological distance collapsed. The goddess became a world, and yet the wonder did not diminish. If anything, it deepened. Seeing the moon as a real place, with mountains and plains and craters, with rocks that could be touched and soil that could be scooped, made it more marvelous, not less. The photographs of astronauts standing in the lunar landscape, with Earth hanging in the black sky behind them, are among the most iconic images ever created. They speak to something fundamental in the human spirit. That spirit is the drive to explore, to understand, to push beyond the boundaries of the known. It is the same spirit that sent humans out of Africa to populate every continent. The same spirit that drove sailors across unknown oceans. The same spirit that built telescopes and microscopes and particle accelerators, seeking to comprehend the very large and the very small. It is who we are. The moon calls to that spirit. It says, there is more. There is always more. The universe is vast beyond comprehension, and we have barely begun to explore it. The moon is the first step, the closest shore, the most accessible unknown. By returning there, by establishing ourselves there, we demonstrate that the impulse to explore is not a passing phase, but a permanent part of human nature. Some will ask whether the resources spent on space exploration might be better used to address problems here on Earth. This is a fair question, and it deserves a thoughtful answer. The resources devoted to space exploration are a tiny fraction of global economic activity. The entire budget of NASA is less than 1% of United States federal spending. The investments in lunar exploration, spread across years and shared among international partners, amount to a small portion of what nations spend on countless other endeavors. The claim that space exploration diverts resources from more pressing needs exaggerates its scale. Moreover, the benefits of space exploration extend beyond the direct returns. The technologies developed for space often find applications on Earth. Communication satellites, weather monitoring, GPS navigation, medical imaging, and countless other advances trace their origins to space programs. The economic activity generated by the space industry supports jobs and drives innovation. The inspiration provided by exploration motivates young people to pursue careers in science and engineering. And there is something less tangible, but no less real. Space exploration expands our perspective. It reminds us that Earth is a single system, that borders are human constructions, that we share a common fate. The overview effect experienced by astronauts, the sense of Earth's fragility and unity seen from space, has the power to reshape how we think about global challenges. Perhaps that shift in consciousness is worth something in its own right. The problems facing Earth are real and urgent. Climate change, inequality, conflict, disease. They demand attention and resources. But addressing these problems does not require abandoning exploration. Indeed, exploration might help. The technologies for sustainable living developed for space habitats could inform efforts to reduce environmental impact on Earth. The cooperation required for international space programs could build relationships that ease terrestrials' tensions. The sense of shared human identity fostered by space exploration could motivate collective action on global challenges. These are not arguments for ignoring earthly problems in favor of space. They are arguments for recognizing that exploration and stewardship can coexist, that looking outward and looking inward are not opposites but complements. The same curiosity and creativity that send us to the moon can help us build a better world at home. As we approach the end of this journey, let us return to where we began. The moon itself, that familiar face in the night sky. Tonight, if the sky is clear, you can step outside and look up. The moon will be there, as it has been every night of your life and every night of human history. Its face will be the same one that ancient people saw when they first wondered what that light might be. The same one that Galileo saw through his telescope. The same one that Armstrong and Aldrin saw through the windows of the Eagle as they descended to the surface. That face is a record of 4.5 billion years. The dark Maria are frozen seas of lava, erupted when the moon was still volcanically active. The bright highlands are the remnants of the ancient crust, formed when the magma ocean solidified. The craters are scars from impacts that occurred throughout solar system history, some recent and sharp, others so old that they are barely visible. Every feature you see tells a story. The Imbrium Basin was carved by an asteroid strike that sent debris across half the moon. The ray systems around Tycho and Copernicus are evidence of more recent impacts, the bright streaks of ejected material not yet darkened by space weathering. The subtle variations in color reflect differences in composition, clues to the geological processes that shaped each region. You cannot see the far side from Earth, but it exists, a hemisphere of highlands and ancient basins waiting to be explored in detail. You cannot see the polar regions from most latitudes, but they too exist, with their permanently shadowed craters and their precious deposits of water ice. All of this is there, every night, visible to anyone who looks up. The moon hides nothing from us. It displays its history openly, waiting for us to read it, and we have begun to read it. A century of scientific study, from telescopes to spacecraft to astronauts, has decoded much of what the moon has to tell us. We know when it formed and roughly how. We know the sequence of events that shaped its surface. We know about its structure and composition. We know about the resources it holds, but we do not know everything. Mysteries remain, and solving those mysteries will require returning, not just with robots, but with human explorers who can adapt and improvise and recognize the unexpected. The next chapter of lunar science will be written on the surface by people who walk where only 24 have walked before. What will they find? We cannot say for certain. That is the nature of exploration. If we knew what was there, there would be no need to go. But we can make educated guesses based on what we know. They will likely find water ice in abundance, perhaps billions, of tons locked in the polar cold traps. They will find minerals that can be processed into useful materials. They will find rocks that tell new stories about the moon's history. They may find evidence of volcanic activity far more recent than previously suspected. They may find traces of ancient Earth blasted to the moon by giant impacts. They may find things we cannot yet imagine. Each discovery will raise new questions. Each answer will reveal new mysteries. The process of scientific exploration has no endpoint. The moon, for all that we have learned about it, will continue to surprise us. And beyond the moon, the universe stretches on. Mars with its dry riverbeds and polar ice. Europa with its ocean beneath the ice. Titan with its lakes of liquid methane. Exoplanets by the thousands, circling stars we can see on any clear night. Galaxies beyond counting, stretching to the edge of the observable universe. The moon is just the beginning, but what a beginning it is. If you have followed this journey from the first words to these, you have traced the arc of human understanding from ancient wonder to modern science. You have learned how the moon formed in cosmic violence and cooled to become a world. You have seen how impacts scarred its surface and volcanism filled its basins. You have followed explorers as they first reached it with robots and then with crewed spacecraft. You have considered what the future might hold, and perhaps you have felt something of the wonder that drives all exploration. The sense that there is always more to learn, more to see, more to understand. The sense that the universe is vast and beautiful and strange, and that we are privileged to be able to explore it. That wonder is available to anyone who looks up at the night sky. It does not require a PhD or a space agency budget. It requires only curiosity and attention. The moon is there for everyone, a companion to our planet, a witness to our history, an invitation to our future. So tonight, if you can, step outside, find the moon in the sky, look at its face and remember what you have learned. Remember that those dark patches are seas of lava cooled billions of years ago. Remember that those bright regions are the original crust, dating to the moon's fiery birth. Remember that humans have walked there and will walk there again. And remember that you are part of this story. The story of creatures on a small planet who looked up and wondered and eventually reached out to touch the sky. The story of lunar science is the story of human curiosity, persistence, and imagination. It continues today, and it will continue tomorrow, and it will continue as long as there are people who look up and ask, what is that? Where did it come from? And can we go there? The moon waits, as it has always waited, patient and unchanging, keeping its secrets close until we come to ask the right questions. It has watched over Earth for 4.5 billion years. It will watch for billions more, and perhaps someday it will look down on a world where its secrets are known, where its resources are used, where its surface is home to human beings who call it not a destination, but simply home. That day may be far off, or it may be closer than we think. Either way, the journey continues, the story unfolds, and the moon, our constant companion, lights the way. Thank you for joining me on this exploration of the moon and the science that has revealed its wonders. If you enjoyed this journey through the cosmos, consider exploring more of our content. The universe is vast and full of stories waiting to be told. Until next time, keep looking up, keep wondering, and keep dreaming of the day when the moon is not just a light in the sky, but a place where we truly belong. The silence of space holds something profound. In the vacuum between Earth and moon, there is no sound, no air to carry vibrations, only the emptiness through which light travels unimpeded. Yet through that silence, electromagnetic waves carry images and data, connecting two worlds that have danced together since the solar system was young. The spacecraft came in generations, each more sophisticated than the last. Crash-landing probes sent back images until impact. Soft landers deployed instruments. Orbiters mapped every crater in detail impossible from Earth. And finally, crewed missions carried human eyes and hands and minds to a place that had only been a light in the sky. Each step built on what came before. Each mission answered questions and raised new ones. Consider what we have gained. We know that the moon is not a failed world or a captured asteroid, but a piece of Earth itself, torn away in a cataclysmic collision and reassembled in orbit. We know that its surface is a museum of the solar system's violent youth, preserving craters from an era when bombardment was far more intense than today. We know that water exists in its permanently shadowed regions, a resource that could support future exploration. We know that its interior is layered and complex, the product of differentiation processes that operate on all rocky worlds. This knowledge enriches our understanding of planetary science generally. By studying the Moon, we learn principles that apply to Mercury, Mars, and the countless rocky worlds we will never visit in person. The Moon is a natural laboratory, a place where we can test ideas and develop techniques that extend far beyond its grey plains. But knowledge is not the only thing we have gained. We have also gained something harder to define: our sense of possibility, an expansion of what we believe humans can achieve. Before 1969, no human had ever stood on another world. The Moon was as unreachable as the stars. Then 12 people walked on its surface, and everything changed. The impossible became possible. The dream became reality. That transformation matters. It tells us that our ambitions are not limited by what has been done, but by what we have the courage to attempt. If we could reach the Moon with 1960s technology, what might we achieve today? The Artemis generation will carry this lesson forward. Young people today will grow up knowing that humans are returning to the Moon, not as a brief visit, but as the beginning of a permanent presence. They will see astronauts walking on the lunar surface, collecting samples, deploying instruments, building the foundations of a sustainable outpost. They will know that space exploration is not a historical curiosity, but a living endeavor, something happening in their own time. Some of those young people will become the astronauts, engineers, scientists, and mission planners of the future. They will carry the work further, to the Moon and beyond. The cycle of inspiration and achievement will continue, as it has continued since the first humans wondered about the world around them. The Moon has been called a stepping stone to the stars. This is true in a practical sense. The technologies and experience developed for lunar exploration will enable missions to Mars and the outer solar system. But it is also true in a deeper sense. The Moon represents the first step out of the cradle, the moment when humanity begins to extend its reach beyond the single world where it evolved. Whether that extension continues depends on choices we make now. Space exploration is not inevitable. It requires investment, commitment, and sustained effort over decades. It requires international cooperation in a world often divided by rivalry. It requires balancing immediate needs with long-term aspirations. The path forward is not guaranteed, but the potential rewards justify the effort. A future in which humans live and work on the Moon, in which we have access to the resources of the solar system, in which we understand our cosmic context far better than we do today, that future is worth striving for. It offers not just scientific knowledge and economic benefits, but a sense of purpose and possibility that enriches human civilization. The Moon has been our companion since before humans existed. It will be our companion for billions of years to come, long after individual lives and even civilizations have passed into memory. By returning to the Moon, by learning its secrets, by using its resources, by making it a second home, we join our brief human story to something far grander, the story of the cosmos itself. Every night the Moon rises. It traces its ancient path across the sky, waxing and waning as it has since the solar system was young. Its face shows the scars of impacts and the frozen seas of long-dead volcanism. Its light touches every corner of Earth, illuminating forests and deserts, cities and oceans, sleeping children and restless dreamers. And somewhere, perhaps even now, someone looks up. A child in a city sees the moon through a gap in the buildings. A traveler in a remote place sees it climb above the horizon. An astronaut on a space station sees it glowing against the black. They all see the same moon, the same ancient companion that humanity has known since the first awakening of consciousness, the same world that Apollo astronauts touched and that future explorers will touch again. That continuity connects us across time and space. The moon we see is the moon our ancestors saw, the moon our descendants will see. It is a thread running through all of human history, linking past and future in a single unchanging presence. When we go back to the moon, we carry that entire history with us. Every story told about the moon, every poem written in its light, every dream dreamed beneath its glow, all of it accompanies the astronauts as they descend to the surface. They represent not just nations or space agencies, but humanity itself, the accumulated hopes and curiosities of billions of people across thousands of generations. And when they look up from the lunar surface, they will see Earth, a blue and white sphere, delicate and alone in the darkness. Everything they have ever known, everyone they have ever loved, contained in that small, bright disk. The perspective will be humbling and exhilarating. They will understand, as few humans have ever understood, both the vastness of the universe and the preciousness of our home. That understanding is worth something. It is worth the cost and the risk and the effort. It is worth the years of work and the moments of uncertainty. It is worth whatever challenges lie ahead. Because in the end, the story of lunar science is not just about rocks and craters and ice. It is about us. It is about the human capacity for wonder, the drive to understand, the courage to explore. It is about looking up at the night sky and refusing to accept that the lights we see are beyond our reach. The moon is waiting. It has waited for 4.5 billion years. It can wait a little longer, but we should not keep it waiting too long. There are discoveries to be made, mysteries to be solved, wonders to be experienced. The next great chapter of lunar science is about to be written, and when it is written, you will be part of it. Not in the history books, perhaps, but in the collective human achievement that makes it possible. Every person who looks up and wonders, every child who dreams of space, all of them contribute to the endeavor. The moon belongs to all of us, and all of us are reaching for it. Look up tonight. See the moon as it truly is, a world with mountains and secrets yet to be revealed, a place where humans have walked and will walk again, a companion that has waited 4.5 billion years for us, and know that you are part of a species that dared to reach for it. That is the story of lunar science. That is the story of us.